So now we give another characterization of solvable groups in terms of cyclic groups. So to do that, we first define a subnormal composition series. So you set G as equal to G0. So this G0 contains a subgroup G1, and this G1 is a normal subgroup of G0. Then G1 contains a subgroup G2, G2 is a normal subgroup of G1, and so on. So you have all these normal subgroups. Now notice that this convention is exactly opposite of what we used in solvable groups. We are setting G as G0, and in the end you have identity. So here we have this Gi over Gi plus 1. This is simple. So obviously Gi plus 1 is a normal subgroup of Gi. So you have a factor group. We are saying this factor group is simple. That means it does not have any non-trivial normal subgroups. So the only proper normal subgroup would be identity in this group. So let us give an example. So you have this S4. It has A4 as its normal subgroup. So A4 is a subgroup which is normal. Then this Klein 4 subgroup is normal in A4. And then we have this subgroup which is generated by 1, 3 and 2, 4, which is normal in Klein 4. And then you have identity. So now you can take quotients to show they are simple. So S4 over A4. So S4 over A4. This is C2, the cyclic group of order 2. So therefore it is simple. Now A4 over Klein 4 is C3. So A4 over Klein 4, this is C3. So this is cyclic group of order 3. Then V over this is C2, cyclic group of order 2. And this over this, you have again cyclic group of order 2. So notice that cyclic group of order 2, this is simple, C3 is simple, C2 is simple, C2 is simple, precisely because cyclic group of order 2, order 3, these 2 and 3 are just primes. So they are cyclic group of prime orders, so they do not have any non-trivial subgroups. So notice that if it was a solvable series, then instead of simple we would have written abelian. And you can go back to the lecture on solvable groups. In that we skipped this subgroup. So we were able to skip this subgroup, and we know this Klein 4 is C4. So we were able to write V over 1. We were able to write this V over 1 as cyclic group of order 4, which was abelian, and it was right to have a series like this to skip this part. So you could skip this, like skip this group in solvable, but we cannot skip this in our subnormal composition series, because here we require it to be simple. So we cannot have C4 because C4 is not simple. It has C2 as a subgroup of C4. So there are exact sequences which come from these simple groups. So you can construct them step by step. So you start with this Gn is just 1. You start with Gn minus 1. So Gn minus 1 is contained within Gn minus 2. In fact, Gn minus 1 is a normal subgroup, so you can form a factor group like this. So Gn minus 1, this is naturally contained within Gn minus 2, and then you can form a factor group like this, and then you can go to identity. Again, Gi plus 1 is a normal subgroup of Gi, so you can again form the short exact sequence like this. And then you can look here, you can again form a short exact sequence. G1 is a normal subgroup of G0, so you have G1 going into G0, and you have a normal subgroup like this. Now that means you can construct this group G successively. So you start with Gn minus 1, you extend Gn minus 1 by a simple group. So you extend by a simple group. So this is simple, as we have seen this is simple. So you extend Gn minus 1 by a simple group. You extend Gi plus 1 by a simple group to get Gi. So you have just simple extensions. So these are non-trivial extensions, something very simple. You attaching like a group, but nothing smaller than that can be attached. So this is what we are attaching. So you keep on attaching smaller and smaller groups, and that's how you reach towards G. So G is built by attaching quotients or forming successively attaching simple groups. So you attach simple groups, and that's how you build G. So you form successive extensions by simple groups. So again, a subnormal series whose quotient groups are abelian is called solvable series. So for solvable series we have exactly the same thing, but instead of simple we were talking about abelian. So we have abelian here. So we can say G is solvable if it is built by successive abelian extensions. So here for a subnormal composition series, this G was built by attaching simple extensions. So instead of simple extensions, you're saying attach abelian extensions. So you will get a solvable group. So why are we talking like this? Why do we need this? This is because we want another characterization of solvable groups. Now notice that an abelian group is simple if and only if it is cyclic of prime order. So in fact, we proved this theorem in the previous lecture when we talked about a solvable group is simple if and only if it is cyclic of prime order. And in fact, that same proof carries over for this. Abelian group is simple because in that proof also we reduced solvable to abelian, and then we were able to prove this. So proof of this is included in that theorem. So abelian group is simple if and only if it is cyclic of prime order. So if we want this simple to become abelian, so abelian is simple, then we are saying that the successive coefficients or the successive quotients would have to be cyclic of prime order. So we say G is solvable if and only if for one of the composition series, and then hence every. This hence every comes from another important theorem we will talk about. So for one of the composition series, the quotients are all cyclic groups of prime order. So instead of simple you want abelian here, then all these quotients have to be cyclic of prime order. So because you want these quotients to be abelian, and abelian is simple, that means you will have to have these quotients of cyclic of prime order. So this G is solvable if it has series like this, and each of these successive quotients, so each of these quotients here, each of these quotients are cyclic groups of prime order. So obviously you can see, if G is solvable, you have this cyclic group of prime orders here, then G1 is solvable because this composition series you have for G, you also have for G1 going like this. You also have for GI, G2 and so on. So you can stop this series at any point starting from here. You can stop it right here and say, okay, G1 is solvable because this condition will again hold. GI is solvable, say, because this condition again will still hold. So you can have these solvable groups. So you have a series of these solvable groups because the successive quotients here would be cyclic of prime order. So this is important because this will be used later on. We will be using both these criteria, that GI over GI plus 1, this is abelian. We will use this criteria for solvable groups. So one criteria is it is abelian, and we have now shown this abelian plus simple gives you another criteria for solvable groups, that these are cyclic of prime order. So we will use these two criteria for solvable groups. So now we are saying that G is solvable for one composition series. The quotients are cyclic groups of prime order. So instead of for one, we say that this will be true for every composition series. And why it is true for every composition series, that comes from the theorem of Jordan-Holder. So the theorem of Jordan-Holder says this. So say you have two subnormal composition series. So G has one series like this, G0, G1 all the way to Gn, and Gn is identity. And you have another series which is H0, H1 to Hm, which is identity. Then the length is the same, m is equal to n, and the quotient groups. So you have these quotient groups which are simple because we are just talking about subnormal composition series. So the quotient groups are simple. So the quotient group of this series and this series, they agree. And they agree up to isomorphism. So that is, you can permute the indices I so that you can get this J here. So after permuting indices. So this will become more clear when we see the proof. So the length is the same, and the components, these attaching components, basically G gets built up by the same components like this. So as we have seen this, that G is getting built up by attaching successive components. You first attach this, so on, you keep attaching the forms like this, then you attach this group, and finally you have this group. So you keep building G by attaching these simple groups, and this is the same thing here.